does there exist an autonomous differential equation with continuously differentiable right-hand side such that the function y equals t minus sine t is one of its solutions? Now, this is a fairly complicated, it's fairly difficult question. So let me try to explain how you could arrive to the answer. So how you could try to reason logically and get the answer. Now, well, since we are working with differential equations, so I think it makes sense to try to plot the graph of the derivative of the unknown function and the unknown function itself. Well, maybe first let me find the derivative. So y prime equals 1 minus cosine t, right? So this is the derivative of the solution. What do we know about this function? So we know that this derivative is always non-negative, right? Because cosine t has values between -1 and 1, so 1 minus cosine t is still non-negative. So it means that at least y is an increasing function. Well, and if you remember, then we have this criterion, so we know that every solution of an autonomous differential equation has to be either increasing or decreasing or constant. So at least that passed. So our function is increasing, so we cannot immediately reject it because of obvious reasons. All right. So, but let us try to see what else do we get. Now, maybe how about we try to plot the solution? So how do we plot the solution? So we know that the derivative of the given function is periodic with period 2 pi, and at the same time we know that y prime of t is 0 if t is a multiple of 2 pi n, right? Because if t is a multiple of 2 pi, then cosine of t is 1, and then we get 1 minus 1 is 0. So the graph of the, so let me plot it here. So the graph of y prime looks like this. So we have, say, 2 pi here, 4 pi here, negative 2 pi here, negative 4 pi, and then it does oscillations between 0 and 2, and I'm sorry, no, this is wrong. So it does this, goes up, then goes up, down, up, down. Okay, this is the correct graph. All right, so it oscillates between the values of 0 and 2, and it takes the value 0 whenever the argument is proportional to 2 pi. Okay, so now let me try to plot. Using this information, I'm going to plot the graph of the function y. So on the plane ty. So what we know is that if this is, say, 2 pi, this is going to be 4 pi, this is going to be negative 2 pi. So we know that if t is proportional to pi, then sine t is 0. So the value of y equals is going to be just the same as t. So this is going to be, say, 2 pi. This is going to be 4 pi. This is going to be negative 2 pi. So our function is, it kind of goes through all these points. It is increasing all the way, and at the given points, its rate of change drops to 0. So in other words, it is something like this. So it goes up, slows down, goes up, slows down, goes up, slows down. So at all points, for all values of t that are proportional to 2 pi, the slope of the tangent line becomes exactly horizontal, because we just calculated it, right? So if we say, let me use a different color. So if we find the derivative of our function at 2 pi, or at 4 pi, or at 0, or at negative 2 pi, they're all going to be 0. So which means that the slope of the tangent line, or the slope of the vector field, is going to be 0, and the vector field is going to, so the vector is going to point exactly to the right. So it is horizontal vector. Right? Now we have just plotted the solution. So this kind of hypothetical solution, t minus sine t. So this is the graph of the function t minus sine t. But now we have not really used the assumption that our differential equation is autonomous. But if we know that our differential equation is autonomous, it means that if we translate this to the right or to the left, then we get another solution. So in particular, it means that, if our direction field is horizontal for some value of t, and when y equals 2 pi, then it's going to be horizontal for all values of t when y equals 2 pi. So it is going to be horizontal for all values of t when y equals 0. It is going to be horizontal for all values of t when y equals negative 2 pi. It's going to be horizontal for all values of t when y equals 4 pi, and so on. All right, so let me write it down. This is extremely important. So this is key to the solution. All right, so since, let me just use 2 pi, it doesn't matter. So since y prime of 2 pi is 0, it means that f the right hand side of my so y prime of 2 pi is 0. So here we have for t equals 2 pi and y equals 2 pi. So we conclude that y prime is going to be 0 for any value of t when y equals 2 pi. So in other words, it means that f of 2 pi has to be equal to 0. But if f of 2 pi has to be equal to 0, then it means that y equals 2 pi is an equilibrium solution. Well, but then let me just plot it. So y equals 2 pi is an equilibrium solution. But at the same time, so this is an equilibrium solution. But this is a contradiction, because now we have two solutions that intersect. So now it means that if we look at the initial value problem, y of 2 pi equals 2 pi, then we have at least two solutions. So y equals t minus sine t, and y equals 2 pi. And this is a contradiction to the Picard-Lindelof theorem. So the Picard-Lindelof theorem tells us that a solution of an initial value problem is always unique. And here we have found two different solutions. So one is the given one, t minus sine t, and the other one is the constant 2 pi, that comes from the assumption that the differential equation is autonomous. And because of that contradiction, this is impossible. So therefore, there does not exist such an autonomous differential equation.